So, we have been considering so far unidirectional transport, where there is variation in the temperature, concentration or velocity field in one dimension, one spatial dimension and possibly in time. So, first we considered transport in a Cartesian coordinate system, where the surfaces of constant coordinates are planes perpendicular to the z direction, and then we looked at a curvilinear coordinate system. Curvilinear coordinates, where the surfaces of constant coordinate in our first curvilinear coordinate system, the cylindrical coordinate system, were surfaces at constant distance from an axis, and these were used for problems with cylindrical symmetry such as the flow in a pipe. Okay. In this case, we will consider a spherical coordinate system. In this case, we will consider a spherical coordinate system in which the surfaces are surfaces of constant distance from a point. Okay. In which the surfaces are surfaces of constant distance from a point. Okay. So, if I have a 3-dimensional coordinate system x, y and z, and the origin is the center of the sphere. Okay. Then if I take a spherical surface in this coordinate system, every point on this surface has a constant distance from the origin r, okay, or the equation for the surface is square root of x square plus y square plus z square is equal to r. Okay. That is the equation for the surface, and therefore, if I wanted to solve for the transport in a configuration that is spherically symmetric, diffusion from a particle or heat transfer to a particle, for example, then I would, in a Cartesian coordinate system, I would have to impose the boundary condition at a constant value of this square root of x square plus y square plus z square, and as you can see, that is going to be an inconvenient thing to do. So, therefore, for problems with spherical symmetry, what you would prefer to do is to have one of the coordinates as the distance from the origin. Okay. One of the coordinates is a distance from the point, okay. And therefore, the surfaces of constant coordinate are spherical surfaces. Okay. The surfaces of constant coordinate are spherical surfaces. Okay. And in this coordinate system, we have to first derive the conservation equations and then use those in order to solve problems, okay, in this spherical coordinate system. So, I will first go through the derivation of the conservation equation, and then I will consider the methods of solution. The methods of solution, firstly, at steady state, the equation will reduce to an ordinary differential equation, therefore, you can solve it directly. For unsteady problems, we will look at different methods of solution, the similarity transforms and the separation of variables. Okay. So, let us first do a balance equation, okay, in a spherical coordinate system. Okay. Okay. So, I take a coordinate system. Let us say for diffusion from a particle into a fluid, okay, as a concrete example. Okay. So, I have a particle, okay, and I want to find out what is the variation in concentration around this particle of radius r, say, okay, around this particle of radius r. Okay. With some boundary condition at the surface of the particle, c is equal to c naught and c is equal to c infinity far away, okay, from the particle. okay, or the temperature could be T naught and T infinity, okay, any of those. So, first we have to do a differential balance over a differential volume. That differential volume is between two surfaces of constant coordinate. Okay. That differential volume is between two surfaces of constant coordinate. Surfaces of constant coordinate are surfaces of constant r. Okay. So, that differential balance is between two surfaces of constant coordinate which are located at r and at a small increment in this, okay, a small increment in the coordinate which will be r plus delta r. Okay. The thickness in this case will be delta r. Okay. The thickness of this volume will be delta r. Okay. So, it is for this volume that we will be doing a differential balance. Okay. This is bounded by two surfaces. There is a surface at r whose surface area is 4 pi r square. Okay. Okay. The surface at r plus delta r whose surface area is 4 pi into r plus delta r the whole square, and the volume is equal to, okay, 4 pi r square delta r. Surface area times the thickness is the volume. Okay. So, we would do this the same way as we did for the cylindrical coordinate system. The balance condition is that change in mass in time delta t. Okay. Change in mass within this differential volume is going to be equal to the mass at time t plus delta t minus the mass at time t. Okay. Mass is equal to concentration times volume. Okay. So, it is going to be equal to the concentration at r t plus minus the concentration at r t, okay, times the volume. Okay. Okay, that is the change in mass in a time delta t. Okay. Mass in is coming in at the surface at r. Okay. Okay. Mass in is coming in at the surface at r. Okay. The flux is considered positive if it is in the direction, same direction as increase in r. Okay. Flux is considered positive if it is in the direction of increasing r. Okay. So, therefore, a positive flux at the inner surface increases the mass within this differential volume. Okay. The positive flux at the inner surface increases the mass. Okay. So, mass in, okay, is going to be equal to C of R T, sorry, it should be the flux, okay, J R at the location R. Okay. Flux is mass per unit area per unit time. So, I have to multiply it by the surface area, okay, 4 pi r square and multiply it by delta t. Okay. So, that is the mass in a time delta t. Okay. Is J r at the location r times 4 pi r square times delta t. A positive flux at the surface r plus delta r results in mass leaving the differential volume. Okay. A positive flux at r plus delta r results in mass leaving this differential volume. Therefore, the mass out is equal to J r at r plus delta r into 4 pi into r plus delta r the whole square times delta t. Note that in this case the surface area does depend upon the coordinate. Okay. The surface area does depend upon the coordinate. Okay. So, the surface area at the surface r plus delta r is larger than the surface area at the surface at r. Okay. So, the surface area does depend upon the coordinate. Okay. And finally, I can have a mass source, okay, production of mass in differential volume. Okay. the production of mass in the differential volume. This is equal to the production rate per unit volume. So, this production is due to, for example, chemical reactions. The rate of production will be proportional to the volume and proportional to time. So, therefore, it is going to be equal to volumetric source per unit volume per unit time multiplied by the volume 4 pi r square delta r times delta t. So, use the balance equation, change in mass in a time delta t is equal to mass in minus mass out plus the production of mass in that time delta t. Okay. So, if I substitute that into the balance condition, I will get C of r t plus delta t minus C of r t, okay, 4 pi r square delta r is equal to j r at r times 4 pi r square delta t minus j r at r plus delta r times 4 pi into r plus delta r the whole square delta t, okay, plus the volumetric source term, which is S 4 pi r square delta r delta t. Okay. So, this is the balance condition. Okay. Just substituting all of these into the balance condition, that change in mass has to be mass in minus mass out plus the production in this differential volume. From this balance condition, I get the difference equation by dividing throughout by volume and time. Okay. I divide throughout by volume, that is 4 pi r square delta r, and divide throughout by time, okay, to get the difference condition, which will give me C at r t plus minus C at r t divided by delta t is equal to j r at r times 4 pi r square minus j r at r plus delta r. Okay. These 4 pi's I can cancel out everywhere, okay, because there is a 4 pi common factor in all the terms. Okay. So, I do not have to include the factor of 4 pi here. So, times r square minus j r at r plus delta r times r plus delta r the whole square. Okay. I divide throughout by r square delta r, okay. Divide throughout by r square delta r, okay, plus S. Okay. When you divide by volume divided by time, you just get S as the source term, source per unit volume per unit time. Okay. And if you examine the first term in this expansion, okay, if you examine the first term in this expansion, okay, it is a function at r minus a function at r plus delta r divided by delta r. Okay. So, if I take the limit as delta t going to 0 and delta r going to 0, in order to get a differential equation from the difference equation. Okay. If I take the limit delta t going to 0 and delta r going to 0, I will get partial c by partial t is equal to, here I have the difference in a function at the location r minus the location r plus delta r. Okay. So, this is going to be equal to minus of partial by partial r of r square j r. Okay. D by dr of r square j r is the value at r plus delta r minus the value of r, okay, divided by delta r, and in addition to that I have a 1 over r square, okay, which I got by dividing throughout by volume. Okay. So, this is 1 over r square plus S, okay, where S is the source. Okay. Now, I can substitute for the flux Gr the constitutive relation minus d partial c by partial r, okay. And the equation becomes partial c by partial t is equal to minus 1 by r square d by dr of, sorry, there is no negative sign here, okay, because I have two negative signs. So, these will multiply to give you a positive sign, okay. R square r square times d times partial c by partial r plus s. Okay. And if the diffusion coefficient is the constant, I will get partial c by partial t is equal to d by r square partial by partial r of r square partial c by partial r plus s. Okay, so, that is going to be the equation if the diffusion coefficient is a constant. Okay. So, this is for a concentration field. Okay. This is for a concentration field. Okay. The equation for the temperature field will be identical by partial T is equal to 1 by r square d by dr of r square alpha partial T by partial r plus the source by rho Cp. Okay. This is assuming that rho and Cp are both constants, okay, as we usually assume. Okay. If in addition the thermal diffusivity is also a constant, then I will get partial T by partial T is equal to alpha by r square d by dr of r square partial T by partial r plus Se by rho Cp. Yeah. And you can see that the differential operator in the spatial coordinate, this one, this differential operator in the spatial coordinate, okay, is different from what we had for a Cartesian coordinate system. There it was just d square by dz square, and it is different from a cylindrical coordinate system, 1 by r d by dr of r times dt by dr. Okay. So, in a spherical coordinate system, this is because the surfaces of constant r are surfaces of constant r are spherical surfaces. Surface area is proportional to r square. If you recall, in a cylindrical coordinate system, it was proportional to r. That is why I had 1 over r d by dr of r times dt by dr. In a spherical coordinate system, it is proportional to r square. Therefore, I have 1 over r square d by dr of r square dt by dr. Okay. So, this is the conservation equation. Okay. Let us proceed to obtain a steady solution for this conservation equation. Okay. The simplest case that you can think about is to have a spherical particle, say, with temperature T is equal to T naught at the surface r is equal to r, okay, and T is equal to T infinity far from that surface. Okay. That is the simplest case that one can consider. Okay. So, my differential equation is 1 by r square d by dr of r square dt by dr is equal to 0, okay, in this particular case. And I can use scaled variables, okay, r star is equal to r by r, okay, t star is equal to t minus t infinity by t naught minus t infinity, okay, which means that the surface is where r star is equal to 1, and at that surface T star is equal to 1. Okay. Therefore, the boundary conditions are at r star is equal to 1, T star equals 1. Okay. The second one is as r star goes to infinity, okay, T is equal to T infinity, and therefore T star is equal to 0. Okay. Far from the spherical surface, T star is equal to 0. Okay. And the differential equation becomes 1 by r star square d by dr star of r star square dt star by dr star is equal to 0. Okay. And I can differentiate it by I can integrate it 1 by 1. Okay. So, I just multiply throughout by r square and this term will disappear. So, this gives me r square dt by dr is equal to a constant, okay, if I integrate it once. Okay. Therefore, dt by dr is equal to a by r square. Okay. Therefore, t is equal to minus a by r plus b. Okay. The boundary condition t is equal to 0 as r goes to infinity implies that this constant b is 0. Okay. Implies that this constant b is 0, okay, because t has to go to 0 as r goes to infinity and a by r goes to 0. Okay. And the second condition that t is equal to 1 at r is equal to 1 implies that a is equal to minus 1, because at r is equal to 1, t is equal to 1. Okay. Therefore, the final solution for the temperature T star is equal to 1 by r star. Okay. Or if I write it back in dimensional form, I will get T minus T infinity by T naught minus T infinity is equal to r by r. Okay. That is the dimensional equation. Alternatively, T is equal to T infinity plus T naught minus T infinity r by r. Okay, so, those are different ways of writing the same equation. What is the heat flux at a distance r from the origin? Okay. What is the heat flux on a surface at a distance r from the origin? Okay. Qr is equal to minus k partial T by partial r. Express it back in terms of dimensional form, minus k into T naught minus T infinity by r into partial T by partial r star. Okay. And since T is equal to 1 over r star, okay, since T is equal to T star is equal to 1 over r star, I will get the flux Qr is equal to minus k into T naught minus T infinity by r times r star square. Okay. When I take the derivative, so let me do it in 2 steps. Okay. Okay. D by dr of 1 over r is 1 over minus 1 over r square. Okay. So, this becomes equal to minus k into T naught minus T infinity by r into minus 1 over r square. So, I can remove this negative sign and I just get r star square. And since r star is small r by capital R, this just becomes equal to k into T naught minus T infinity by into r by r square. what is the total heat transfer rate? Okay. QR is equal to 4 pi r square times the flux, surface area times the flux. The heat transfer rate at a distance r is the surface area times the flux, okay, is equal to 4 pi k into T naught minus T infinity into r. Okay. So, now if I substitute, okay, for T naught minus T infinity in terms of r, okay, if I substitute for T naught minus T infinity in terms of QR, okay, I use this relation to express the difference in temperature in terms of the heat transfer rate, okay, that is T naught minus T infinity is equal to QR by 4 pi k r. Okay. I express the temperature difference in terms of the heat transfer rate. Okay. Then I will get this is equal to T minus T infinity is equal to into, okay, which is the total heat transfer rate divided by 4 pi k r. Okay. That is the total heat transfer rate divided by 4 pi k r. Okay. Okay. Note that when we express the temperature, okay, the difference between the local temperature and the temperature at infinity in terms of the heat transfer rate QR, okay, when we express it in terms of the heat transfer rate QR, okay, the expression turns out to be independent of the sphere radius. Okay, the expression turns out to be independent of the sphere radius. So long as the distance from the origin is greater than the radius, right, the difference in temperature between the location r and infinity depends only upon the total heat transfer rate. If you had particles of different sizes, if the heat transfer rate is the same, then the temperature is the same at a location r from the origin. Okay. So, when expressed in terms of the heat transfer rate, the temperature becomes independent of the particle radius, okay, for a spherical particle. Okay. And what that implies is that even if I take the limit of the particle radius going to 0, r is equal to 0, right, if I take the limit of r is equal to 0, when the particle shrinks to a point, so long as the heat transfer rate is the same, the heat generated per unit time, that is the heat transfer rate from the particle, that is the total heat transferred from the particle per unit time. So long as that is the same, the temperature is the same. Okay. We will look a little bit at this concept of the heat transfer rate from a point particle in the next lecture, before we look at conduction from a spherical shell. So, in this case I have derived for you the conservation equation in a spherical coordinate system and solved that conservation equation for the simplest case of a particle with a constant temperature at the surface. I will give you some more physical insight into this solution in the next lecture, before we look at heat conduction in a spherical shell, okay, that we will continue in the next lecture. I will see you then.